font size good?
For me, yes.
Yeah.
Okay. Okay, then let's continue.
You're taking my job.
Sorry. So let's continue with identity types. That was the point we previously stopped at. And so we will talk about identity types, and I think we will discuss like the rules for it and how it works. And there are different variants of identity types, different versions of identity types, and this is actually one of the most important distinguishing features or distinguishing like point in different type theories. So we will talk about this. And all right, but before we are starting, so there was this question, so should we make this seminar 1 hour? Or because there will be an Agda implementors meeting talk by Jesper after 1 hour. So if some people are interested, I'm interested. For example.
Yeah, my vote is to just do a 1 hour thing.
Yeah, let's make 1 hour then.
Okay, let's make 1 hour, and then I will only talk about identity types probably in that 1 hour. So I will not go forward with some models. I think the last time we mentioned some family model or some pre-shift model, and probably I think 1 hour will be filled with identity types. Okay, so I hope that everyone roughly remembers like all of this stuff. Maybe let's just write down a very few basic components here. Just the context, substitution, terms, and types, just as a reminder. And then we look at identity types, and I thought that it would be also good to just write some Agda. So there are a bunch of examples when it is a lot easier to write Agda code than to write informally. Okay, so what do we want to express with identity types? Basically, we want to have a notion of like a type for equality proofs. Such that we can use it for internal equational reasoning. So that internal reasoning with equalities. Because so far we've seen like a number of different type formers. So we've seen that we have a pi type, we also have a sigma type, and we've seen natural numbers and bools and unit type and bottom type. And it is true that if you only have these kind of type formers, then what we are doing can already be viewed as some kind of logical formalization. And I'm not sure like how much should I talk about this Curry-Howard like encoding or representation of logical statements. So should I talk about the representation of logical statements, or is this something that most people here are, or everyone here are familiar with? Because I don't think
from the name I'm not, but maybe if you write an example, it will just come back to my mind.
Okay, so the idea is that all of these previous type formers, so these previous type formers that we've seen before, maybe not and bool, but these are definitely, so you can view this as ways to represent logical statements as well. So this is a types can be viewed as logical statements or propositions. And for example, if I have the implication, then it's the non-dependent function type. So I say that if I have a function from A to B, then I view it as a proof that A implies B. I'm not sure how to denote this logical thing, but maybe let's also just use the same kind of arrows. So the function type, maybe I can write it a bit nicer. So just let's just make a table. So there are types, and there are also like logical formulas. And if I have a type which is a function which goes from A to B, then it's the implication. Okay, how can I write it in Agda? I'm not sure. Okay, so this is implication. And if I have, so the type, so the A times B, so this is the non-dependent function type here, and this is the non-dependent sigma type here. So this is just a pair type, and I can use this to model a logical conjunction, and I can use this type which we haven't seen on this seminar, but we know it from Haskell. This is the sum type, and the sum type is a way to model logical disjunction. And if you have a dependent function type, then it's like this. And if you have a sigma type, then it's like this. So is this familiar to you, Vispi, or still not familiar?
The first three is. I think I've seen the other ones too, just it wasn't named pi type or sigma type that way because it was something maybe more concrete, but yeah.
Okay. Okay, then let's move on to identity types. Okay, thanks for the pointer for notation. And the identity types would be, so an IDA of TU is the thing which we want to specify now. And this would correspond to the logical formula which says that T equals U, where T has type A and U also has type A. So if you have a system for working with logical formulas, so if you have a proof system for a logic, then there are ways of using proofs of these formulas. And those generally correspond to the elimination principles. So in type theory, we have a function and we can apply it. In logic, we have a proof of an implication, and we can use the modus ponens rule to do a very similar thing than in type theory. And here we have a pair type, and we can use the first and second projections. And here we can also use axioms, which say that whenever we have a proof of a conjunction, then we can extract proofs of the first and second formulas. And likewise, so there is a kind of a correspondence between types and logical formulas, and this is exactly the way how Coq and Agda works. So in Coq and Agda, whenever we want to prove a logical statement, we write a type, and the proof will be a term. And now we want to also introduce equality proofs. So there will be ways of constructing equality proofs, and there will be also ways of using equality proofs. But first, let's just start with the type formation. So I say that ID is basically I take a type in a context, and I take, and I also have to name this, for example, A. So I have an A, which is a type in gamma, and then I have a term with type A, and I also have a term with type A, and then this is a type in gamma. So basically, this is a type former depending on two terms. And if I write something like, let's just use a comment like this. And if I write something like ID of not and M, then if I have a P which has for example a type TM gamma ID not and M, then this means that logically this means that assuming gamma, I have a proof that N and M are equal numbers. So this would be like a logical Curry interpretation of having an inhabitant of this particular term. So gamma is all the hypotheses, and this is the statement, and the statement says something about the equality of numbers. So I have a type formation, and I have like the introduction or construction rule. And the construction rule is called REFL. And REFL says that whenever I have a T of some A type, then I can actually prove the identity of TT. So this means that everything is equal to itself. And this is called REFL because it says that this is the reflexivity rule of equality. Okay, and there is also an elimination rule, but this is a bit complicated. So I think, so like with, for example, with natural numbers and Booleans, we can have dependent elimination rules, and we can also have non-dependent elimination rules. So I think it's a good idea to first only look at the non-dependent eliminator. And in the case of Boole, the non-dependent eliminator is the if then else. So it's just a way of doing the case distinction on a Boole. And in the case of equalities, the non-dependent eliminator is something which is also called like the Leibniz principle, which says that basically if we can prove two things to be equal, then we can always substitute one thing with another in any other context. So this is also called like substitution, but this can be a bit confusing because we already have another notion of substitution, but this is very specifically substitution of equals in any context. Okay, and for some reason, this is usually called transport, but you shouldn't worry or you shouldn't think too much about this name. So this transport is it comes from homotopy type theory, but it refers essentially to the same principle, that if we have an equality proof, then we can transport any construction from one thing to another thing which is equal. So let's call this transport, and it says that if we have some type which depends on another type, so we have this B type which depends on another type, and we can represent this dependency by saying that this is a type in a context which is extended by an A type. So we have some dependent type, and we also have some here. Let's just do some kind of implicit quantification. One moment. Yeah, so let's say that we also have these two terms with type A. So this is kind of an Agda notation for these implicit arguments. So I'm introducing here this TU here. And I also have a proof that TU are equal. So I have a proof that in A, TU are equal. Then if I have a term which has type B, but B where this A is substituted with T. So I have a Tm gamma B, where I have a B IDT. Then I can also get a Tm gamma, where B is instead substituted with U. So this means that in any dependent type B, I can swap T for U. But only, or in general, I can do this if I can prove that T is equal to U, and I can prove this equality using the identity type. And just quickly, let's also mention some substitution rules. So of course, with REFL, we still have this substitution rule. So if REFL is substituted, if REFL T is substituted with any sigma, then this is the same as REFL and T substituted. Yeah, so the substitutions for constructors are always kind of mechanical, because all that happens is that the substitutions are pushed inside the parameters of the constructor. And likewise, here we have a substitution rule for transport. And so I have a transp of B, and also have like this T U. Let's not write them. So let's name this P. So this parameter should be called P. So the transport of B, P, and BT, and so I'm giving the name BT for this parameter because it has type B substituted with T. So if I take this thing, and if I'm applying some substitution, then like before, what happens is that I have to push the substitution inside. But here, this B is in an extended context, so I have to use the previous trick, which is to use this plus, which lists a substitution into. So basically, you can review this from the previous. I'm not sure which one seminar, but here I have to use this lifting operation on substitutions, and the other parts are simple. Okay, but I think it makes a lot of sense to just look at a bunch of examples in Agda. So we will look at some examples in Agda as well. And I also have a beta rule for transport. So this says that if I'm using a transport, but the equality proof is actually REFL, so if the equality proof is reflexivity, then I can just immediately return this. because if the equality proof is reflexivity, then the two terms are exactly the same. So this operation, which substitutes equals for equals, can be reduced to the identity function. Balázs, I think the Agda talk will start at 1 p.m. and we decided to end the seminar now at 1 p.m.
Yeah, but I think it's already going actually on Twitch. But
is there maybe a previous talk?
Well, there is only one talk in the homepage. This is Jasper Cox talk.
Oh.
But you can probably watch it after on Twitch. I think it's
Which time zone? Does it say any time zone on the Agda implement?
UTC 10 o'clock.
UTC, so we are UTC +2.
Yes, so that's 12. And it's already going. There is some talk going on Twitch.
All right. Okay, then another option is that we just continue now the seminar and then we can later watch the Agda talk, or do we want to immediately head to the Agda talk? But are you sure that it's recorded?
I think Twitch auto records things and you can watch it for 2 weeks or something, everything. I hope so.
Okay.
Yesterday's talk is recorded.
Okay, then what should we do? Should we then do this seminar, or I think so?
I suggest that you just continue and let's hope it's recorded.
Okay. Then I say we can continue the seminar and then we can also make it a full duration, so we don't have to finish earlier. Then of course. Okay. Okay, then let's continue. If someone wants to participate in actively participate in the Agda implementor meeting talk, then those people can leave, right? Okay. So there is a computation rule for this transport, and it says that if I have a transport of B refer T of BT, then that just computes to BT. And we can check that the size of these equations are the same. So if we are having a refer T here, then on the left-hand side, we will have, because refer T has type ID of T and T, then on the left-hand side, we have a Tm gamma B IDT. And likewise, on the right-hand side, we have exactly the same. So this computation rule is well typed. But let's look at some Agda code. So I'm just importing the equality type, and I will just define this transport. But like the imported stuff and the defined stuff is not so interesting. But what will be more interesting is to just use this transport and REFL to try to prove some things. Okay, let's also import some natural numbers and some booleans. And let's define this trans. Let's call it exactly the same way as in these notes. So a transport we have, and now there is a slight difference in how we would write this in Agda, because in Agda it is convenient to say that a dependent type is just a function which goes into the universe. So in Agda it is a lot more convenient to say that I have some A, which is a type, and I also have some B, which is a function.
Sorry, just one moment. What's the propositional equality import? Is that the id? Or?
So yeah, it's the id, but but let's also make it a bit nicer. So I say that I'm renaming this to a what's the problem here? Now it's good. Yeah, so it's defined slightly differently in the library, but I just renamed it to it. So it's going to have the same name as before. Okay, so in Agda, I'm just defining this function. This is not a built-in operation. So if it were a built-in operation, then it would look a bit like this. But now I'm defining it, so the types are a bit different, because here I'm defining some definition with the function type, and the way I can talk about dependent types is by using the set, which is the universe. So let's also so it's a universe in Agda, but I can also say that U is defined to be set. So let's do it. So it's universe in Agda. And then if I have some TU, but let's call them XY instead, because now we are not really talking about terms. So here we are talking about terms, but here we are just talking about some kind of variables in Agda. So if we have these terms, and if we have a proof that ID of X and Y, and we have a B of X, then we can have a B of Y. And I also have to open everything. Okay, there is a slight notation. So here in the ID, the A is also implicit, but I can also write it out. Okay, maybe I cannot write it out.
Well, you can if you want to. You just have to write as A equals A, because otherwise.
Yeah, but it's ugly. I could redefine ID, but I think now it's going to be fine if I only be A. Okay, so if we have B and P and B of X, and this definition is you don't have to look at it. This is basically just a definition in Agda, but this is not strictly speaking related to our discussion. So let's just say that this is transport is some primitive operation. Yeah, and now we are kind of so the question, is this rule actually a good rule? So if only have the transport as a way of using an equality proof, then is this enough? And it's enough for a lot of things. So for example, we can derive from transport that equality, so ID is an equivalence relation. Because we already have like referrals for reflexivity, so that's okay. But we still need symmetry and transitivity. And it turns out that symmetry and transitivity are just provable. So symmetry says that if I have an ID of xy, then I also have an ID of yx. And this works for any A, which is a set, and any xy, which is in A, which are in A. Okay, so if I have a sim x, y, p, but now The challenge is that I can only use transport because I say that transport is the only available elimination principle for identity. So here I have to do some transport. And what can I do? So transport allows me to have like any inhabitant of a bx type, and from that get an inhabitant of by. So I have to choose this b some way so that the transporting is does what I want the result to be. So the challenge is always to kind of make a choice of b such that I can use this b to get what I want. So I say that I want to transport and here if I look at this p, so this p has type id x of y. So what happens, for example, if I want to do this? So now this is a type which depends on this y, and this is this id x of y, when this x is something which comes from like the outside, from the outer scope, and this y is what is bound here in this dependency in B. So can I make this work? So what happens if I say this? This looks pretty good because now I only have to write in this like this remaining position. I only have to write an equality proof for IDXX, and I already have an equality proof, which is reflexivity. What's the problem? Oh, it's the other way around. Yeah. Okay, let's just think about it. I kind of forgot, so I have id x of y, and I want id epsilon of y, and with transport I can place.
So B is gonna be flip of ID in this case, right?
Sorry?
So B is gonna be flip of ID.
Flip of ID, but it still needs one argument. Oh no, it doesn't. So I want to go from. I'm sorry. I'm usually I'm an expert, but now I'm probably low on blood sugar. Just have to think about it. So x to y, then I just want to replace x y. No. No.
Why do we have that 0
Maybe
after the...
Don't call the binder x. That's confusing.
You need to flip x and y.
Shoot.
But then the base case.
So the result should be id yx.
Yeah, the result should be id yx.
So you should bind either x or y and write id.
Yeah.
X.
So the goal. Now it's good. Now it's good. Okay. Okay. Let's look at it again. Okay. I got confused because I thought that transport works in a different way than the dependent eliminator, the order of arguments, but it doesn't really. Yeah. Okay. Sorry. Okay. And now I remember like what is the general principle of using transport. So let's break it down a bit. So here I want to prove. So Agda tells me that the goal is id yx, and I have a proof that x is equal to y. And in general, the way of using transport is that if I have an equality proof, then it lets me rewrite in the goal type something from right to left. So basically, transport by P allows me to rewrite this goal along an equality from right to left, so I can rewrite a y to some x. So so here the goal is id yx, and transport by p basically allows rewriting x to y, so it always goes from right to left in the goal. So here, if I am using instead the transport of no, sorry, because I have a proof of idxy, I can rewrite y to x. So transport by p idxy allows rewriting y to x in the goal. So I can here, if I write idxy p, then indeed did I screw up again? So p is yes. Yes, because the goal is yx. Sorry. Yeah, so if I do this, then the goal just becomes idxs, and I can use referral. So here, the goal is idyx, and here the goal is idxx. Yeah, so this is symmetry. And there is also transitivity. So if I have a set, and if I have an x, y, z, again, an id xy and an id yz, and I also have an id xz. And now I have some a, some x, y, z, and some pq, and I want to return an equality proof. Okay, and now I can, in the goal type, so in this goal type, I can rewrite z to y, and I can also rewrite y to x. And in this case, I want to search for like particular rewritings, which makes the goal type trivial. So for example, or not trivial, but solvable. So for example, if in the goal type, I rewrite z to y, then it becomes xy, and xy is already available as a proof. So that's one possible thing which I can do. So I say that transport, and I want to rewrite z, and I'm using this q proof. And now the goal is just id of xy, so I can use q. So this is one possible way of proving it, but there is also, this is maybe a homework, do instead trans on p. So do it the other way around, and then it also works. And there is also a third version, and the third version is to do trans on both p and q. But they are all pretty simple. Okay, so here we know that identity is an equivalence relation, but this is kind of still a non-dependent. Okay, let's do maybe another example, which is called up, and this is the congruence. So this says that ID is a congruence for functions. Okay, it means that if x is equal y, then for any function, it will be true that f of x is the same as f of y. So this is also quite interesting because So it's one thing that equality is an equivalence, but I also want to know that equality is respected by every function in my type theory. So it would be very useless if I can actually prove some equality, but then do some other constructions which actually do not respect this equality. So if I have an A set and an XY, an A, and I also need a B set and a function which goes from A to B. So for any function and for any identity proof, I want this identity to be preserved by the functional application. Okay, and now I can use this equality proof and transport to rewrite y to x. So if y becomes x in the goal, it just becomes ID of fx and fx, and that can be proved. That can be proven by reflexivity. So I can use transport of, and I can just copy paste here the goal type and p, and now the goal becomes essentially just this reflexive equation. So I can use REFL. Okay. And before looking at the dependent elimination principle, let's look at this question. So the question, so are ID proofs unique? So is there an eta rule for ID? Because we already see that there is a beta rule for transport. But the question is, if I have an equality proof which has the same things on the left and the right sides, so then is that equality proof REFL? So the question is, if I have some equality proof of TT, then do I know that this is the same thing as REFL? So the question is P the same as REFL? And now I am using an identity type of an identity type. So here the A type is IDTT. So it would be a bit like an eta rule. So this is seems kind of plausible because there is only one way of doing. So there is only one constructor for ID, and it is called REFL. So then the question is, if I have some ID which has the right type, then is that identity proof the same as REFL? But here, the thing is that this is not provable. We don't look at the reasons, but this is not derivable from what we have. And this will be like an important variation between different type theories. So it's an important variation between type theories is whether UIP is part of the system or not. And some type theories have UIP, and some other type theories, they do not have UIP.
So I have a question. So for previously defined types, it seemed that the eta rules were, like whatever we wanted them to be. They were by fiat. So how?
I don't think that's the case.
Well, but they certainly weren't derived from other rules.
I think it's so the previous eta rules are quite justified, because the eta rule are just part of a type formula which is given as an isomorphism. So that basically the pi type is defined or specified as an isomorphism, and the sigma type is also just specified as an isomorphism, likewise the unit type. So every type former which is specified by isomorphism automatically includes an eta rule because there's just one direction in the isomorphism. But the bool, for example, was not defined by an isomorphism. So we didn't say that Tm gamma of bool is somehow isomorphic to. So because bool can be viewed as like the sum of top and top, then we did not say that there is such an isomorphism that this is isomorphic to the meta theoretic plus of Tm gamma top and Tm gamma top. But we did say that Tm gamma of sigma AB is isomorphic to a sigma of terms, and then the sigma is a meta theoretic sigma. So I think so whenever we are defining or whenever we specify a type with an isomorphism, then that gives rise to an eta rule, and otherwise, yeah. Okay, but this is actually a very good point for continuation. So let's just write a note. So for types given by isomorphisms, we always have eta. So the question is then, so can we specify ID as an isomorphism? So can we do this? And we expect that if we do specify ID as an isomorphism, then there will be an eta rule, and then the eta rule will be pretty much the same thing as UIP. And actually, yes, we can do, and then we get UIP as part of the isomorphism. So we can do something like Tm gamma of ID ATU. So is it isomorphic to the meta theoretic? So like this. So here on the right hand side we have meta theoretic equality of T and U. So T and U are just particular terms, and we can talk in the meta theory about equality of particular terms. So can we do this? So what about this? And if we do this, then it means that yeah. So we still have REFL. So REFL is one direction. So one direction is REFL, and REFL basically gives us from any proof in the meta theory that the terms are the same. So if I have a proof in the meta theory that two terms are the same, then I can use the meta theoretic substitution principle, and so it's pretty much this REFL. When I say that for any T and U, so such that they are equal in the meta theory, I can give a Tm gamma of ID of TU. This is the same as the old REFL. And the other direction, so the other direction is that if I have a Tm gamma of ID TU, then can I get a meta theoretic proof that these terms are equal? And this is not. So we haven't introduced this before. So this is a new thing. And this is called equality reflection. So equality reflection is the principle that and we can also give it a name, so let's call it reflect. So this is a principle that if we have an equality proof in the type theory, then actually we have a meta-theoretic equality of terms. And right? And if we also know, that that this is basically an isomorphism. So if we know that refer and reflect form an isomorphism, then we also get UIP. And pretty much the same way as before. So that's part of the.
And that's true even if the meta theory doesn't have UIP.
Even if the meta theory doesn't have UIP, actually, no. Is that correct, Rafael? So if the meta theory doesn't have UIP, then we don't get internal UIP. Is that correct?
I think that's correct. Yes.
Yeah. Yeah.
I mean,
okay.
you would expect not to, right? Because you would expect it to somehow inherit the properties of the meta theory, the equality if they're isomorphic.
Yeah. Okay. So yeah. So okay. So it's a good question, and yeah. So we get UIP, but only if the meta theory has UIP. Yeah. So if you have an isomorphism which goes out to the meta theory, then the identity type inherits the properties of the meta theoretic equality and inherits UIP. But if the meta theory doesn't have UIP, then it doesn't inherit UIP. Okay. So we have this, and so if we have reflection. So if we have reflect plus UIP, then it's called extensional type theory. And if we only have kind of dependent version of transport, which we will see, if we only have dependent version of transport, but we don't have reflect, and if we don't have UIP, then it's called intentional type theory. Yeah, so of course we have refer in every case. So we have refer here. Then it's called intentional. So this is the difference between extensional type theory and intentional type theory. But the naming is also kind of just a legacy naming. So yeah. So in reality, we have lots of intentional type theories which are more extensional than extensional type theory. So it's just some terminology which you should probably remember, but this naming is not super descriptive anymore. Okay, but there is an important property of ETT. So the property of ETT, which is a bit problematic from a practical standpoint, is that basically type checking is undecidable. So type checking and like meta theoretic equality of terms. So equality of terms, types are all undecidable. Of course, if we say that equality of terms and types is undecidable, then type checking must be undecidable as well, because in type checking, probably you can see that sometimes we have to compare terms and types for equality, and if equality is undecidable, then type checking is undecidable as well. Okay, and why is this the case? So why is ETT undecidable? And I can give some intuition, and then I can also give a concrete proof, not a fully formal proof, but a more or less complete proof that of undecidability of ETT. So the intuition is that the reflection rule basically it doesn't. So the reflection rule kind of hides information. So it doesn't contain enough information to allow kind of so basically, okay, so the intuition is that ETT does not have enough annotations. So it's a kind of a general phenomenon is that you have, for example, you have a surface language in a programming language, and you want to do some inference, or you want to recover some information which is implicit, like you want to infer implicit arguments or functions and so on. So you have some surface language, and you want to compile it to some core language which is more explicit. And if the surface language does not have enough annotations, then sometimes this is not possible. So it becomes an undecidable problem because there is too much information is missing. And in some sense, ETT has a similar problem, because the reflection rule in ETT allows us to essentially omit transport. So the reflect rule allows us to omit transports. Maybe we can also look at some example for this. So, for example, so let's prove symmetry using equality reflection. So I want to prove some. Let's also just use the Agda notation. So if I have an A set, and if I have an xy in A, and if I have a P in ID of xy, then I want to prove ID of yx. All right. So x, y, p. Let's do an extended comment block here. So I want to prove this thing, and previously I had to use transport, but now reflection. So reflection says that as soon as I have any term, as soon as I have anything in scope which proves t equals u, then in an external sense, t is the same as u. So the reflection rule says that as soon as I have p id xy in scope, x and y are freely interchangeable without having to use transport. So the equality reflection rule says that if there is anything in the scope which proves an equality, then the two terms are just exactly the same, because in the meta theory we have a proof that they are exactly the same terms. So now I don't even have to use transport. I can just return P. And likewise, if I am writing constructions in extensional type theory, I never have to use transport. I only have to bring some equations into scope, and then everything happens kind of auto-magically. So basically, T and U are kind of identified in the meta theory. Okay, but this is a bit problematic, because this means that whenever I have to do any proof which works by equational reasoning, I don't have to write the proof. So it happens kind of in a magical way. And you can imagine that it is undecidable to automatically generate any kind of. So it is undecidable in general to have some proof and erase some equational reasoning from the proof, and then just say that just try to automatically get it back.
So is it a bit like okay, so when you say the type checking is undecidable, it might sound esoteric, but of course everyone can easily imagine situations where type inference is undecidable. Like there's nothing weird about that. And is the case here that type checking would involve some kind of equality inferring, and that's the thing that you can't do automatically?
Yes. Okay, I mean, so I don't agree that type inference can be undecidable. I think type inference should be also decidable. It's just that type inference is not complete. So type inference is not able to infer everything, but there is some restriction which makes it decidable, but at the cost of completeness. But in the case of extensional type theory, so if you are writing proofs which don't have transports, then it is an undecidable problem to try to recover all the transports from that.
But if you make this distinction, couldn't you also say that type checking is just incomplete because there are, like, you could restrict terms to the things where there's no identity types ever in scope, and you can do type checking.
Also, so you say that so could I have an incomplete procedure to try to get back the transports, which is decidable?
Yeah.
Yes, that would work. But I think so. The big problem. So the problem with ETIT. So the problem with equality reflection is not necessarily that so the problem with equality reflection is not that it's undecidable. Okay, it's a problem that it's undecidable, but the problem is that it doesn't give us any clue how to recover transports. It just completely forgets everything about transports and equality proofs. And if you want to just write an algorithm which kind of works naively or by brute force, it will be a very, very crappy algorithm because equality reflection just gives us no hints. But so I'm contrasting this situation to, for example, like a cubical or setoid type theory, that actually transports can disappear in many cases, but the whole system gives us like a lot of relevant information about how transports are computed away. But equality reflection gives us no clue whatsoever. So the problem...
I don't understand what you mean by transports being erased or recovered. Isn't the whole point that we can prove stuff that is not provable by transport? So what does it mean to recover transport for something that has no proof using transport?
No, I mean we cannot prove. So if you have transport and UIP, then we can prove everything which can be proved by equality reflection. Okay, we also need function extensionality, but basically equality reflection does not give us any extra proving power. if you already have some other basic principles, like if you assume UIP and FunX, then equality reflection is conservative. So it doesn't give us proving power. It only.
That I still don't understand. Then how can you not recover? The proof that it's conservative is an algorithm, isn't it? That that recovers the transports.
Oh, okay, this is getting a bit, complicated, but so if I'm writing some syntactic object which doesn't have transports, then that kind of object has undecidable equality, and recovering the transports is also undecidable. But it is is the syntax which we usually write informally. So informally, we use ETT to write proofs which are really clean and nice because no transports are needed. But then this kind of notation, this kind of ETT notation is undecidable. So you can write your proof like this and it will be very, very nice, but there is no algorithm which can check that it's actually valid. But we can also write another kind of ETT notation. And another kind of ETT notation is when basically thing is annotated by meta-theoretic transports. Because here I am saying that I'm writing something in the syntax of ETT, but whenever I use reflect, I have to mention a meta-theoretic equality proof. And this is actually the kind of notation that we get if we formalize ETT in Agda, for example. And if we look at this kind of notation, that it is decidable, but it is horribly big, and it's even less convenient than working in intentional type theory. So, and the conservativity proof, so the conservativity, which says that everything provable with trumps UIP. Okay, so everything provable in ETT is already provable with transport UIP and FunX. So here, this conservativity statement, it refers to this kind of ETT proofs. So like these fully explicit ETT proofs, which are embedded formally in some meta theory, such that the meta theoretic equality proofs are also completely formal. Okay, yeah, this is a bit complicated, I admit.
It's complicated, but it was very useful for me, so thank you.
So here's what I don't understand, because I'm sure everyone's just dying to learn what I don't understand. So here's what I don't understand. So you mentioned that in like cubical type theory, we track a lot of extra information in the equalities, and that's why we don't have this problem. But of course, that's because in homotopy type theory, we have all these interesting equalities. So there is information that is good to have around, and then in cubical type theory, we carry that information around. But here we have UIP. So what is the information that we need? Like what do I care how two things are equal if the only way they can be equal is by being the same? So then what is the extra data that we miss when we use ETT?
So what you are talking about now is basically the point of setoid type theory versus ETT. So setoid TT.
Well, no, okay. So what I'm saying is that
setoid TT has UIP, but in setoid TT, the number of transports is dramatically lower than in intentional type theory with UIP. Setoid TT also has more information related to computing transports, but it just computes transports which are always trivial in the meta-theoretic sense. So yeah, it's a bit weird because if we are working in intentional type theory with UIP, then all the transports and all of the equality proofs are already trivial, but we cannot omit all the transports because then we get an undecidable syntax. And the problem with ETT is that ETT doesn't give us any hint how to omit the transports in a decidable way. So but when we switch to setoid TT, then it gives us a system which is kind of rigorous for a way of decidably computing transports away and omitting them.
But again, so that's in a setting where the equalities are not trivial internally, right? Because you have setoid, so I assume you must have.
No, they are trivial. So in setoid TT we have UIP, so they are still trivial. So the equality is in strict prop in setoid type theory. So in setoid TT and ETT, so basically, in both cases, so equality proofs are unique and irrelevant, but setoid TT has a way of decidable, systematic kind of computation, elimination of trans, and ETT does not have any such way. So ETT just works by magic if you are using the informal notation. Is this a good answer for this question?
Well, I mean, it still doesn't tell me what that extra. If we have UIP, then what is the extra info that we ever need? Like even in ETT, what like intuitively, if there's only one way for things to be equal, why do I need to know how they are equal?
Okay, but here the interesting part is not the equality proof. The interesting part is the transport. So I want the transport.
But isn't the same transport? Like you can only transport trivially if you only have trivial, I mean, equalities, right?
Yeah, but if you say that every transport is trivial, then it's magic. So you get the same thing as in ETT, and it becomes undecidable. So I can give a concrete example, which is a way of omitting a transport in setoid type theory, right? So in setoid type theory, I can have something like a coercion by. So I mean, I'm doing a coercion. So the coercion says that if I have some two types, and I know that ID AB, then I have a function from A to B. So this is a special case of transport. And one example when a coercion just disappears in setoid type theory is when I say that a koi from bool, or maybe not. Okay, let's just write just two random arbitrary types. So koi ABT. No, sorry. So koi list of A to list of B, P of nil A is definitionally equal to nil of P. If we assume some list type and the nil has a set list of A, for example. So here we have a transport in set OTT which disappears by computation. And for every inductive type, we have like computation rules which look like this. And we also have this coercion computation for functions and for sigmas and for universes as well. So we have a bunch of computation rules like this. And all of these rules essentially try to eliminate the coercions from open expressions. And it's a systematic way. And in ETT, it doesn't really work. And in intentional type theory, this is an equation which has to be proven by hand. And then we can use even more transport to transform expressions along this equation.
Okay, but that's because so is it true to say that the problem only comes once you start using equalities between types, so IDU?
No, because I can also rewrite this computation rule with transport, and it's still pretty much the same, even if I don't refer to U. So I don't need to use universe. So I can also write like a transport of and this is a transport which doesn't require universe. So this is kind of a primitive transport, and then I can say something like, here I have a type which depends on a type. So this is an A dot, like a list of A which binds A. So this is not a lambda, so I don't have to talk about the universe. And then a transport A dot list of A. And then I have this P, and the P has type ID. Okay, with the list example, you always need an equality between types, but we don't necessarily need such thing. For example, we can also transport like a vector from one length to another. So if I want to coerce like a vec of A of suc M to a vec of A of suc M, and then here I have some proof that suc of n, so here I have this maybe of suc p, and then I have like a cons of x and xs, then it's computes the cons of x and p, like a m, like a m, p. So this is coercion without equality. Okay, so here we have an equality in the universe, but now I can rewrite this as a transport.
But you get this property if you just say that trans of cons x-axis is equal to cons x-axis, because it couldn't possibly be anything else if the identity can't do anything fancy, right? So that would still satisfy this equation.
So what would satisfy this equation?
So suppose that I had a rule that just that the transp of x is equal to x. I mean, okay, transp of b p x is equal to x.
But then it's not well typed yet. So it's only well typed with equality reflection, right? Because on the left side I have something which has type b of t, and on the right hand side I have something which has type b of u.
Yes, but that's exactly what I'm getting at. That if we are in ETT, then we do have equality reflection, and as long as we don't have universe level equalities, do we still get into trouble? Like, I guess what I'm asking is if we were to take ETT minus equalities in U, would that be decidable?
No. Okay, let's give a so here I thought some intuitive reasons why ETT is not decidable. But let's look at a concrete example, or maybe concrete proof of undecidable equality of ETT terms. Okay, so how does it go? So let's just take a typing context. Okay, so what's the idea? So the idea is that I specify some like the rules of SK calculus, which is Turing complete. And the computation rules are given by ID. And now I can put the rules into some gamma context, and Tm gamma A basically. So Tm gamma ID of like this SK term something. Okay, I don't even have to mention this. So I only have to mention this. So there will be terms of this SK calculus in this gamma context, and if I have a TU with this type, then deciding
I can
equal U requires basically deciding a Turing complete system. Right? So
okay, I think that answers completely my question.
So I can say that this context has like, let's call it maybe, let's just call it T, which is in U. So here I'm using a universe, but I think this somehow also works if I don't want to use a universe. So there is a T in U, and there is an application of T. Let's write it in infix, like this dollar T. And this is the internal function type, and I could also write out all of the ELs. And then I have an S rule and a K rule. There's a K rule which goes from T, then there's an S rule which goes from ELT. And let's just delete the ELs because they are kind of annoying. So I have K and I have S, and I also have a K beta rule, which says that if I'm applying K, there is a missing argument here, I think. So K of T U equals T, and there is similarly there is a MS rule which says that as G FGT is I think this is right now.
I think K and S should be of type T.
Which should be of type T?
K and S.
Oh yeah.
Type
Right.
T.
Right. I don't have to do this expansion, but this is still this type. Yeah. So if I'm working in this context, then so in this context, so Tm gamma T as undecidable equality. Okay. And I can put anything. I can put any other undecidable equational theory. So I just have to choose any undecidable equational theory for gamma.
And how does this relate to equality reflection exactly? Because
So,
I get that SK.
So the way it relates is it's only undecidable if we have reflection, because if you have reflection, then so only undecidable if we have reflect. And why? Because if we have reflect, then every ID proof in gamma yields a meta-theoretic equality. So whenever I have a P which has type Tm gamma of ID T something like Tu, then let's also write out the types of T and U. So T are Tm gamma T, right? So this implies that T is equal to U, right? So the reflection gives us a way of equating two terms in the meta theory from any internal equality proof. And if we don't have equality reflection, then we don't have this implication here. And if we don't have this implication, then it can be shown that actually then this is decidable, because then it's just like normal type theory. So if I don't have equality reflection, then it doesn't matter what kind of proofs I can write with this type, because that has no bearing on whether in the meta theory I have an equality of terms. Is this a good answer?
Yeah, so basically the undecidability of the SK calculus implies that if equality would be decidable with reflection, then SK would also be decidable, right?
Yeah. So from reflect, it implies, so reflect implies that Tu is decidable if Tm gamma ID T Tu is decidable. But we can very easily show that Tm gamma ID T Tu is just the equational theory of SK calculus. So this is undecidable. So this must be undecidable as well. Okay.
Yeah.
Okay, so where to continue? I think we should continue now. So this should conclude the discussion, or at least conclude the discussion for now. This reflection and extensional versus intensional type theory. So let's look at the dependent elimination for ID. So in every elimination rule, so for example, going back to bool, so in the case of bool, the non-dependent elimination was just if then else. But the dependent elimination allowed some dependency on bool. So it looked like if we have a type which depends on bool, let's call it P. So if we have a type which depends on bool, and if we have a term which has type P true, so there is some type which depends on the bool, and if we can prove this P for true, and we can also prove this P for false, then we can take any B, which is a Tm gamma bool, and we can also prove P for this P. So this is the dependent if then else. So the non-dependent if then else is just a way of doing recursion on bool, and the dependent one is a way of doing induction on bool. So we want to prove some statement, and we have to consider two cases: when the bool is true and when the bool is false. And likewise, the transport. Let's copy the type of transport. From here. So transport says that, so this is kind of a recursion principle on ID, because I have a type which does not depend on the type of identities. So I have a type which does not depend on ID, and I just want to write a non-dependent function which goes from ID tu and b of t to b of u. So this is a kind of a recursion principle for identities. But there is also an induction principle for identities, which is called J. And the way this J works is that if I have a type which depends on a gamma, and here I think probably I should use a nameful notation, or even better, I should just use Agda, because it's going to be a lot clearer if I'm just writing the definition of Agda than if I'm trying to write out all of these ties and TMs and all of these substitutions as well. So let's just write it in Agda. So if I have a type, and if I have some P which depends, okay, not yet. So if I have a type, and if I have an element of the type, and then I have a P which depends on an equality proof such that the left-hand side is fixed to be this particular element. So I have a P which depends on an equality proof. So an ID xy set. So P depends on an ID. So this is, I want to prove something about an equality proof.
Why doesn't P depend on X?
It could, and then it would be a different version of J, and we will also look at that different version. But this is kind of the standard version of J. And we will look at the other version as well. Yeah, so if we have this, and if we can show P for REFL, so if we can show P for X and REFL of X, then for any Y and P in index Y, we can also show large P of YP. So if P can be proven for raffle X, then P can be proven for any P. This is kind of the idea of this induction principle. And like for the other induction principles, so here with Boole, if P can be proven for the two constructors, then it can be proven for anything. Here, if P can be proven for raffle, which is the only constructor, then it can be proven for any P. Okay, let's just define this. So we have a P, and a P raffle, and a Y P, and yeah. So here we are just using a pattern matching, but also let's just assume that this is a built-in operation. Okay, and now the question is, and we also have a beta rule for J. So the J beta is just this. So here, this pattern matching definition, which I can write down in Agda, and we can just consider it as the J beta rule. And it's pretty much the same as the beta rule for transport. So transport computes if the equality proof is raffle, and likewise J computes if the equality proof is raffle. Okay, and now the question is why do we even need J? So if we only have raffle plus trans, but we don't have UIP. So what kind of equations or what kind of constructions which are possible with J, but which are not possible with only transport? Yeah, so do you have any ideas? So when is a situation in intentional type theory when I want to prove something which depends on an inequality proof?
Well, any kind of proof which assumes that two things are equal, I guess. Yes, right. If we are defining any kind of proof relevant thing which depends on an equality proof. So if you write any kind of computationally relevant function which goes from like A to B, but not all of A, but maybe only some kind of, or maybe it goes from A to A to A, but yeah, but so basically if we have any function such as A to A, and then maybe I have a function from A to B, and I want to have some condition like f of A is equals to something, and then I get some results. So any kind of computationally relevant thing which depends on equality proofs, if we want to prove things about those functions, then we have to use J. But there are pretty simple examples, and the simple examples is when we want to prove something about the behavior of transport itself. Like when I was talking about these computation rules for coercion, so if I'm transporting a list, then this is a rule that I have to prove if I want to reason in intentional type theory. So whenever I have a list and I also have some transported lists, then I want to know how this transport behaves. And that's one point when I have to use J because I have something which depends on an equality proof. But an even simpler example is like how transitivity computes. In some cases. So I can show that, that if I have a trans of P and a raffle, and I want to prove that this is the same thing as P, for example. So I want to show this. So if I have an A, which is a set, and I have a P, which is an ID of XY, then of course I also need an X and a Y. So XYA and P in ID of XY. For example, I want to prove that this equality proof is the same as P. And then I can use J to prove this. But you are also asking, okay, why do you want to prove that an equality proof is equal to some other equality proof? But the motivation for that can be is that sometimes maybe I want to show, that some P is raffle, because if P is raffle, then transports disappear. So this is one possible motivation for doing proofs about equalities, because if I can show that some equality proof is raffle, then I can use it to make some transport disappear, and transport disappear, then that probably makes work easier. Okay, and this reasoning is in intentional type theory. So now we are only assuming transport J raffle, or we are only assuming J raffle and the computation rule for J. Okay, so if I want to prove this by J, then what I can do now is that J makes it possible to, in the goal type, replace Y with X, but also replace P with raffle. So basically, J allows me to rewrite P to raffle in the goal. So now the goal now the goal is actually trivial, because the way I defined trans, you can see that trans is defined by transport on the second argument. So if this is defined by transport on the second argument, then this equation just holds by definition, because you can see that the goal here is ID of trans P raffle of something, but trans P raffle is defined by a transport, and the transport does a transport on raffle and immediately computes away. So this particular equation can be just proven with raffle. But if I do it the other way around, then I don't have this computation rule automatically anymore. So then I have to do proof. So here I have ID of trans ID XP raffle equals P. And here I want to rewrite in the goal P to be raffle. So I say a J, and then I have a lambda YP. And this. So I'm just writing a dependent type here, and the dependent type depends on Y, but Y is actually does not explicitly appear here, but it also depends on P, and P does appear here, right? So now I only have to write, so here I have to write the Y, I have to write P, and now I can just write raffle. So J allows me to rewrite some p id xy to referral x in the core type. And this kind of reasoning is very common. So this reasoning is really important if you are working without UIP. So in intentional type theory. I mean, it's not super interesting, but it's kind of necessary, and it becomes more interesting if you are working in homotopy type theory. So just a quick word about homotopy type theory. So homotopy type theory, basically it adds axioms which are incompatible with UIP. So basically axioms which allow more interesting equality proofs to be constructed. So in HOT we can do some equality proofs which are actually not just refer. So HOT in many cases allows us to do an equality proof which is not just refer, but which is some more interesting, more general kind of identification of two things. For example, in HOT we can say that two types are equal not only if they are exactly the same type, but two types two types also equal if there is an isomorphism between them. So AB. Two types are not only equal if they are the same, but also if they are isomorphic. And an isomorphism is a kind of it's a back and forth mapping. And this is a pretty big topic. So identity types in type theory is a very big topic, and actually like a very significant part of all research on type theory is somehow related to identity types. So identity types kind of like the biggest point of divergence when we are studying different flavors of type theory.
Okay, I have to ask at this point, can they coexist? Can a type theory have two ID types that satisfy a different subset of these principles, or will they just be forced to coincide by?
So this is a good question. So the question is, can we have maybe two different IDs? And if you are not doing more tricks, so if you are only saying that, okay, we have two identity types and one identity type has UIP and the other one does not, then they are forced to be the same identity type. So we cannot just simply duplicate ID and say that, okay, one has UIP and the other one does not, because this ID is kind of defined by a universal property. So if you duplicate it, then you can just prove them to be isomorphic as types. Likewise, if you have like two booleans and the two booleans both support the
elimination principle for Booleans, then you can just prove them to be isomorphic because it's defined by this universal elimination principle. So if I say that one identity type has transport and UIP, so if I say that ID has transp and UIP and ID1 has J but no UIP, and actually we can show that ID0 is equivalent to ID1, and thereby UIP is basically transfers to ID1 as well. So we cannot do this simple thing, but what works is if we have a two-level type theory. Then we say that we essentially have two universes plus kind of a lifting rule or lifting construction from U0 to U1, and then we are allowed to have an ID1 which is in U1, which is in U1 with UIP, and an ID0 in U0 without UIP, and then this works.
And so these U0 and U1 are two distinct universe hierarchies?
You can. I mean, so if you want to have like the simplest version of two-level type theory, we just say that we have two universes, U0, U1, and that's it. But you are right that if you want to have like the usual universe levels, then the usual universe levels are orthogonal. So we have double indexing because universe can be indexed by level 1 and level 2 in this way, but universes can be also indexed in the usual way, and then we have level like U00 and 01 and 02 and so on. But
and then we can lift from U0i to U1i, but we cannot lift from U02 to U11, for example.
U0, so what? So from U0 to?
So we can lift the level. I mean this binary level, but not.
Okay, so let's just say that we have Uij, and I is just 0, 1, and this is for two-level type theory. Two-level theta levels, and we also say that J is just natural numbers and this kind of usual universe hierarchy. And then in two-level type theory, we would say that there is a lifting operation which is very specifically about going from this 0 to this one. So there's a lift which says that if I have some A which is a type, or maybe, so this lifting operation is not a function internally, it's a built-in operation in the theory. And if I have some A which is in U0i, then lift of A is in U1i. Yeah, and plus there is a rule that every elimination principle stays in the same I level. So if I'm working in U0, then I have an elimination for natural numbers in U0, and I can only eliminate into the same level. So this is the kind of the crucial ingredient of two-level type theory, because otherwise it would be just a normal universe hierarchy
But if I do this restriction that every elimination principle stays in the same I level, then it behaves a bit differently. And in particular, it allows us to have different identity types in different levels.
But then you said that transport and UIP is equivalent to just simply J.
Right.
And then what's the difference between these two identity types in this two-level type theory? Because one is just with UIP and the other is just without UIP. But I assume that J there.
So if I have transp, so transp plus UIP implies J. However, J does not imply UIP, right? So if I have, sorry?
Right. But then they are not equivalent, right?
No, they are not equivalent.
Oh, okay. But you said that they are in line.
No, here I'm just saying that just so here we are only specifying two ID types. Okay, maybe we can also call it, because here there are no universe levels involved. We just say that there are two ID types. Maybe one is ID and the other one is ID prime, and we specify that one ID has transport and UIP, and we specify that the other one only has J, right? So here we are just specifying this. So like for every other type former, we are just saying that there is a type and there are some eliminators. And here we say that there are two different flavors of ID, and we give transp and UIP to one flavor and we give J to the other flavor. But in this case, we can just show that the two IDs are equivalent to each other. So they are like the type of ID TU is isomorphic to the type of ID prime TU. So that's why if one has UIP, then the other also has UIP.
So the difference is, just to clarify what Andreas said, if you have a type theory that has an ID with transport and UIP, and another type theory that has J on its identity type, then they're not the same type theory. If you have a single type theory where you have an ID type which satisfies transport and UIP, and another ID type that satisfies J, then your type theory proves that these two are in fact equivalent types and both satisfy all of these principles.
Oh,
that makes sense?
Yeah,
Yes.
yeah, that makes sense.
Yeah.
Okay,
Yeah.
so only if both are present, then it's somehow like it's like complete. So we can prove that both support basically J and UIP and everything.
Yeah. So one way to think about it is that UIP just infects the other identity type in this case.
And what if we had like two identity types, but without bringing UIP into picture? Could you prove that then that they are equivalent?
So for example, what happens if I say that one have transp and the other have J?
Well, obviously, that's not equivalent.
Do you mean
that yeah, like I mean, we have two different types, but both have J. Yeah.
Yeah, then they are equivalent. So for the same reason that if you are defining like natural numbers twice, then with the same elimination principle, it's the same type. And here I'm defining IV twice with the same elimination principle. It's again, it's the same type up to equivalence.
All right.
And so the problem here is that from transport and UIP, we get J. So these two types are equivalent because this also has J, but unfortunately this also has UIP, so the UIP transfers from here to here. So it kind of infects the other identity type. But if we use these two levels, then this equivalence is not possible anymore. So we kind of quarantine the UIP in the one universe.
And so in this case, the U0 universe level can contain axioms which are incompatible with UIP. For example.
Yeah. So that's a usual use case for two-level TT is that the inner level has anti-UIP axioms and the outer level has UIP. That's correct. In particular, we say that the inner is hot, and usually we say that the outer is ETT.
But it's also possible to reverse this and have UIP in the inner layer and univalence in the outer layer.
Yes. I'm not sure what happens what are the practical consequences if we do this the other way around. And I think it becomes probably a bit limited, because then we want to reason about kind of an inner syntax in a homotopy type theory, but it's kind of weak.
No, I would say it's actually very useful because basically it's a way to get to essentially get univalence for the inner layer, but in a well-behaved kind of way, in a way that does not imply UIP.
Oh,
yes. Because then
yes, I mean for the inner layer we can have an univalent equality reflection, right?
Yes.
Okay, I think the time is up. I'm not sure how to approach like this identity type thing. I personally think the best way to do it is to write lots of Agda code with identity types involved, but it's a bit open-ended. But I'm not sure how to make it a bit more compact, because as I mentioned, this is like one of the biggest topics in type theory, and we can go very far when studying identity types in type theory. So, but I don't think that we are going to do anything with homotopy type theory in the following seminars. So this is kind of just an excursion. So like there are a bunch of different ways of having identity types, but those will not be very relevant. So we will not do anything with principles which contradict UIP. So basically, if you only know about transport and UIP and roughly know how to use that kind of equality, then probably that will be fine. Yeah, and what should be next time? Study of equality. Yeah. Okay, so next time. So the previous time we mentioned, or Ambrus mentions, the previous time Ambrus mentioned inductive types in general. Inductive types in general is also a big topic, so I'm not sure what to continue with. Maybe the next time is Raphael. Maybe Raphael could mention W types, but I leave the choice to Raphael if he wants to mention inductive types in general. I think this could be skipped because
yes, I think so. I'm not an expert in W types.
Yeah, so I think this could be skipped, and we just say that an inductive type is like what you would intuitively expect in the following. but we talked about some other models, some models only mentioned models other than the set model, and I think we mentioned maybe the family model. And I prepared a little bit about the family model, so I thought about how to show refutation of excluded middle and also like parametricity properties. And yeah, but Rafael, you can do whatever you want. But I think the general theme is that it should be some model which is not the set model.
Yeah, but yeah, I think the next model to consider is the family model.
Okay.
Yeah.